Welcome to Part B of Points, Lines, and Planes. Remember, these are the things that we just accept. Points, lines, and planes. What's the difference between a line, array, and a segment? These two have something this one doesn't. Remember, we didn't actually define a line. We assume that we know what it is. We gave a rough description so that you know what we were talking about, but other than that, it's not really a mathematical definition. I explained before why that is, but these are different. These we define in terms of this one. I only mention it because they'll ask things like that sometimes on the standardized exams. I want to make sure you understand the difference between the objects in geometry which are undefined, which is what we're looking at right here, and most everything else which is defined. So if anybody asks you what's the difference between a line and an array, well, a big difference is array is well defined. A line is undefined. And let's make sure we remember what our symbols mean. Remember, a capital letter by itself would be a point. Two capital letters with a little bar over it, that's a segment. And the ST with what looks like a ray, well, that's the ray, ST. And when they put a symbol over it that looks like a line, well, that's the line, FG. It's not a big deal. You just have to remember what these mean, or the problems will be hard to read. And here we have to make sure we can identify our geometric objects. Now, as I said, if we can't identify these things, it'll be hard to talk about and hard to understand the problems. What's another name for ZY? Well, what is ZY? Well, they drew just a segment up here with no arrows. That means we're referring to the segment, ZY. If this were a line, we might be able to say ZV, because any 2 points on a line are good enough to define the line. But the segments, we need the endpoints. We talk about the segment in ZV, we mean it ends right here at V. And that's not what's going on. So, what's the other way to say this? Well, we could just reverse the order. It doesn't matter which order you write them in. So you could write YZ. That would be about it. Now, for all the rays with endpoint B, remember, the ray goes off to infinity in one direction. Only in one direction. So if we put V's right here, that's an endpoint for this ray. It's an endpoint for this ray. It's an endpoint for this one, and for this one. So it's actually a whole bunch of them. We got VW. I should put a little bar up here on top of the YZ to indicate that's the segment YZ. Now VW, that's the ray VW. Normally, we put the endpoint first, VW. WV for array, that's going to be confusing, because if you wrote WV for array, you would think W was the endpoint, and it went off to infinity this way. But in fact, VW is this ray here. Okay, that's one. VX, that's another one. VY, yeah, that works. And VZ. Oops. How about VZ? There we go. In other words, this ray, these are all rays. If you put these two together, you could have a line, but V to W, that's a ray. Now, pairs of opposite rays. Remember, opposite rays, they share an endpoint. So, we've got VS and VZ. I'll write it down here. VS and VZ. That's one pair of opposite rays. The other pair is VW and VX. Those are the two pairs of opposite rays. This VW starts here and takes off that direction. VX starts in the same place but takes off in the opposite direction. Hence, opposite rays. And another name for WV. Well, remember this is a ray, so we can't write VW. That'd be cool, but we can't do it. WV, we're referring now to a ray that's with an endpoint of W, and it takes off in this direction. WV is a legitimate name for the ray that starts at W here. WX is also a legitimate way to label it. So we'd have the ray WX would refer to the same as this. Remember, rays go off to infinity, so the endpoint is important. After that, it doesn't really matter which point you use to define the ray. That's not true for a segment. Remember, the WV and WX would be completely different segments because we identify segments according to their endpoints. Here we have the error analysis. The idea is somebody got something wrong. Not a student. More likely a journalist. Says that VW and VZ are opposite rays because they have the same endpoint. Well, suppose it was like this. Here's V here. And this takes off. And we'll put Z here and W here. Well, these are opposite rays. They have the same endpoint, plus together they form an actual line, and they take off in opposite directions. Suppose it wasn't like this. Suppose it was V here, pardon me, Z over here, and I meant to imply that there's a point over here called Z, not an endpoint, of course. Suppose I got a ray off like that, with W over here. Well, these are not opposite rays. They share an endpoint, that's true, but they're not opposite rays. These are opposite rays, so any two rays which share an endpoint, you can't automatically assume that they're going to be opposite rays. Sharing an endpoint is a necessary condition, not a sufficient condition. You have to share an endpoint in order to be opposite rays. However, the fact that they share an endpoint is not enough to guarantee that they actually are opposite rays. Here's a multiple choice problem. Let's see if we can figure out what's going on here. Which statement about this diagram would be true? A, B, and C are collinear. Well, not quite. As you can see, this looks like a wall and a wall here. You treat a wall like a plane. These two are on the same line, and these two are on the same line. But the three of them, no, two different lines. Or segments, or rays. Either way, they're distinct. So A, B, and C are definitely not collinear. What about coplanar? Let's see here. C, D, well, I got C, D, E, and G. Well, you can see if we treat these walls like planes, which is legitimate, the segment BE represents the intersection. The intersection is in the plane. So C D, E, and G are all on the same plane, and therefore coplanar. So it looks like this one's true. But let's double check and see how the other ones look. B lies on GE. No. Almost. If it said the line GE, then it would be true. But this is the ray, so this is the endpoint, and the ray. The ray, GE, starts here and takes off this way. B isn't part of the picture, so this is false. What about ray EF and ray ED? Aha. EF and ED. Now, these don't take off in opposite directions. These, in fact, well, if this is a normal court, these two walls would be perpendicular. Normally, the walls are at right angles in an auditorium. So these are not opposite rays. These are, if you drew a picture of it, they'd look like this, with the common endpoint here. But as we saw in the previous problem, the fact that they have a common endpoint does not make them opposite rays. So we're left with B is the only statement that we know is true about this diagram here. Okay, now we're given that a couple of lines intersect. I drew a picture of it down here. That's usually a good idea, especially in geometry. Just draw yourself a quick little picture of what's going on. It makes things really obvious. And you could probably do this in your head if you visualize what's happening. But it's not necessary. You can just draw yourself a picture and quickly and easily figure out what's going on. Which of the following are opposite rays? Well, let's see here. We've got ED and EC. And it looks like this one is. What about CE and DE? Well, no. Remember, they at least have to share a common endpoint. In fact, if we go through and look at these quickly, if this were a standardized test, I would say, first check for common endpoints. This is the only one that has common endpoints. So it's probably the only one that has a possibility of being right. Because, for instance, CE and DE, we just look at that, and it doesn't make any sense. How about AB and BA? Well, the ray AB would be the ray that goes from here. It starts here and takes off this way. The ray BA starts here and takes off this way. Remember, for rays, these letters are not interchangeable. For a line, yes, and for a segment, yes, you can interchange them. For a ray, no, it makes a difference which letter comes first. Here, AE, well, wow, that's this ray here, and then BE. Well, these two are rays that are coming in towards each other. I think these two are also. These, well, this is A to B, I see, yeah. These are rays that are coming at each other too. These are opposite rays. So, the first one we saw here, naturally, you probably haven't taken hundreds and hundreds of standardized exams. If this were real, and you came across a right answer, you might glance at these just to make sure you didn't make a quick mistake, but I will spend much more time on these multiple choice problems than you probably would in an actual test where you're pressed for time. And spotting the common endpoint here, that's a quick way to look for possibilities. Doesn't mean that they are opposite rays, but opposite rays have to have this common endpoint here. If they don't, you can strike them out. So all these you could quickly toss out. Okay, and this is just going to give us some more practice on labeling our geometric objects here. Yeah, it seems a little bit boring, but you have to know how to identify these things in order to work the problems, in order to understand the problems, and in order to talk about the problems. It all hinges on vocabulary. If you don't speak the same language, it's going to be hard to understand what it is they're asking you. So let's get started. What about PR and HR? Now we've got our line symbol up here. Not a segment, not an array, but the line. The intersection, two lines, it's going to be a point. So we have HR here. In order to produce a line, we would just extend this and put the arrows on it. We've got a whole bunch more to do, and if I do that with every line, this thing might get too messy looking. Let's see if I can do it without drawing in the arrows yet. Here's HR. Now what about PR? Well, PR is this line here. So what's the intersection? It's just a point, of course. And it is the point R. Now, what about the plane EFG? Which one is EFG? That would be this one here. So it looks like the plane is this top. If this is, you look at this as a rectangular box. This is EFG is the top of the box. FGS, well, that's the right side of the box. What's the intersection? Remember, these are planes. We draw them finitely, but since they are planes, they intersect at a line that takes off to infinity in both directions, because the planes do as well, even though we can't draw it that way. So the correct answer is FG, of course, but is it the segment FG? No, not if we say the plane. If we're just going to take this little section of a plane, okay, then this would be the intersection, and it's a segment. But we're calling these planes, we're representing them finitely because, as I've mentioned 100 times, we can't draw them infinitely. But wow, that's supposed to be that. In other words, we put our line symbol over the FG to indicate that the intersection of two planes is a line, not a segment or array. What about plane PQS? There's PQ and S. So that looks like it forms the bottom part of this rectangular box. And referring to it as a box over and over again seems to imply that these planes are finite. This is just the intersection of these planes. They take off to infinity in two directions. So PQS is this bottom plane here. HGS. That's the back side here. So we have this bottom plane and this side plane here, so RS would be the intersection, and once again that is the line RS, not the segment or the array, the line. Now, our points PQ and F collinear. Well, there's P, there's Q, and there's F. Do they all lie on the same line? No. FQ would form one line, or a segment. I know it's drawn as a segment, but FQ can also be considered a line. We just have to write it that way. For instance, we could write, it's perfectly legitimate to write the segment FQ, because we can just stop it right here. On the other hand, it's equally legitimate to write the line FQ. We just have to understand that now this thing takes off in both directions. But we label them the same almost. The little bar or line up on top is the giveaway. collinear? No. But this is the line here for PQ. This is the line for QF. They are not collinear, so that's a big no. What about P and G? Well, this one's tricky. We've got a diagram here. In a previous question, they asked us if P, Q, and F were collinear, and we used the diagram to see if they could lie on the same line. 3 points don't have to be collinear, but 2 points? Well, 2 points define a line. Pick any 2 points anywhere, just put one there and one there. There's always a line that goes through them. So it's not really possible to come up with 2 points which by themselves are not collinear. They have to be. Are they coplanar? Well, just as any 3 points can define a plane, any 2 points are going to could be placed within a plane, I guess I should say. Although maybe any plane, because remember, 2 points define a line. A line could be in lots of different planes. So, and in this case, P and G, we don't have an actual plane drawn in here which contains P and G, nor do we have a line which contains P and G. But 2 points can always be collinear, and they can always be coplanar also. Name 3 planes that intersect at point E. Well, there's E. What about EHG? That's one plane, right? Notice we don't put a plane symbol up on top here. That would be cumbersome. The fact that we're using 3 letters for now indicates it's a plane. Later on we might have to use some other symbols, put something in front here when we use 3 letters to distinguish it from something other than a plane. But for now, 3 letters means a plane. So EHG would be 1. How about EPR? It's this side here. And then, what about this front piece here? That also intersects. And we can call that EFG. Pardon me, that's a Q, isn't it? Okay. E, F, and Q. Now, when I label these, any 3 points are sufficient to label the plane. So I could have called this one HG. HGF, or EPR, I could have labeled PRH. I just stuck the E in all of them to make it totally obvious that E is a common point amongst all these planes. Yes, let's try another one. Here the idea is to determine if the given point here is on this line. Remember from algebra, this is the equation for a line. For instance, the line y equals x, if we had 2 x and y coordinates, would look like that, right? Now, I'm sure you remember this. Now, these are nice, simple linear functions, or linear equations, or lines. They come with lots of names. The question is, would this point be on this line? The best way to figure that out would be to put in one of these for one of the variables and see if the other variable turns out to be the other one. What the heck did I just say? For instance, if I put in a 1 for y, would x turn out to be 5? If it did, then 5, 1 lies on this line. Or I could put in 5 for x. If y turns out to be 1, then it's on this line. Suppose I put in 5 for x. Just do it right here. Well, gee whiz, I think 5 minus 4 is 1. So the point 5, 1 definitely does lie on the line. Yep, got it. What about this? Does the point 1, 6 lie on this line? Real easy. Let's see. 4 times 1 is 4, plus 2 is 6. So if we put a 1 in here, we get a 6 here. So 1, 6 definitely lies on this line. And that's what you would always do. To see if a point lies on the line, just see if it satisfies the equation of the line. Here's one that's going to show us how to interpret some of these lines, segments, and rays. So they have a nice, well, algebraic number line interpretation. For instance, and this is what I'm using for a number line, just the x-axis of a grid here. So, x greater than or equal to 3. So we've got this here, and just takes off like that. Well, it doesn't go up though, pardon me. That's pretty bad. That's a slightly better looking ray, and that's what we have. X greater than or equal to 3 means it starts here. Everything down here is out. Everything to the right is okay. So that's a ray that just takes off to infinity here. What about x greater than or equal to 5? Or x less than or equal to 2? Now let's take a look. Let's label our points here. 5 is down here. Minus 2. Now, x greater than or equal to 5, that's going to take off like this. X less than or equal to 2, well, that goes in that direction. So, if we graph this, we end up with 2 rays. X. Oh, wait a minute. X less than or equal. Jeepers. I made a big mistake on this one. Well, it was big. It was definitely an opposite kind of mistake. Let me redo this one for you. I completely misread this first one. Gee whiz. X greater than or equal to 5. Did I get this one right? I hope so. And then x less than or equal. Okay. This is all right. Oh boy. If you were yelling and screaming and throwing pencils at the screen, I don't blame you. That was a dumb mistake. X is less than or equal to 3. So it is a ray. At least I got half of it right. But it takes off that way. X less than or equal to 3. Not that way. Sorry. Hope I didn't confuse you. Maybe we should do a couple more like this. Maybe to get rid of any confusion I may have caused with the first one. Let's take a look at 2 more. And these are separate. This is one x greater than or equal to minus 4. And this is an entirely separate graph. So we'll graph this one first. Where's minus 4? It's right here. Now what does this say? X greater than, that's to the right. So this is a ray. Pretty simple. This is, well, it's kind of like the way I did the first one, except that this one's actually right. Now, what about this one here? Well, at the left we've got minus 7. That's, and off to the right we've got 4. Now x has to be less than 4. It takes off this way. But it has to be greater than 7. So this, I just try to draw in a little dotted line there. I don't know what that's about. My pencil slipped. This segment here. this represents a segment. It's not a line because it stops right here and here. And of course it's not a ray because it has two endpoints. This has one endpoint. This has two endpoints. So you see what's going on here. There are simple, you could say algebraic descriptions of segments and rays. This is an algebraic way to write a ray which starts at the point -4. This is one way to describe a segment which goes from 4 to -7. I think you'll hear me say a lot in this class that there's frequently, in fact almost always, more than one way to solve a problem, and there's more than one way to represent an object. We could call this a segment, or we could refer to this. They mean the same thing. Well, here's something that you may have noticed if you've ever seen one of those three-legged milking stools or a tripod. You ever wonder why tripods work? And things with more than 3 legs may or may not work. Take a 4-legged table out into the woods somewhere and try to set a camera on it. Probably won't work very well. Why? Well, any 3 points will define a plane, but 4 points don't. 4 points do not have to lie in the same plane. 3 points always lie in the same plane, which means no matter how uneven the ground is, if you take a tripod and set it down, it will be stable, because the endpoints of the 3 legs will always lie in one plane. They are always coplanar. By definition, they have to be. Any 3 points defines a plane. So the ends of the 3 legs, even if the legs aren't even, I mean, you might have a leg that's like for a tripod, one's 3 feet, and the other one's kind of messed up and only came out to 2 feet 10 inches. Well, it would still be stable. It would tilt a bit, but it would be stable. With 4, no. You don't necessarily have 4 points that are coplanar. 3 points have to be coplanar. 4 points, they don't have to be coplanar. You could have a point that lays off the plane. And in fact, if you're on uneven ground, that's frequently what will happen. This wasn't a complicated problem at all. But I think it's definitely worth remembering and mentioning that 3-legged tables and tripods are stable for a good reason. 3 points define the plane. There's a mathematical reason for an awful lot of the things that you see in day-to-day life. And later on in this course, we're going to show more of that. Why do you put cross pieces under bridges so they don't fall down? Well, you put cross pieces in so they don't fall down, but why do those cross pieces make the bridges stable? I mean, why is it they fall down without the cross piece, but with the cross piece they usually don't? Why is that? Well, stick around, in a few chapters we'll find out why that's true. But for now, this is about it for your introduction to points, lines, and planes.